So, one-dimensional, and what I mean by that is stuff isn't going to be happening at angles yet. We're going to get there in a couple of lessons. Important one-dimensional force problems include the elevator or apparent weight problem, which starts to explain or starts to attempt to explain why you feel heavier while an elevator is on its way up. Or instead of elevators, I'm nuts about amusement park rides. We'll think about why you feel a certain way at the top of the hill or at the bottom of the hill if you're on a roller coaster or on the elevator. The air resistance problem, friction, and the many-body problem. The normal force is the contact force between the floor and an object. It's the force with which the floor pushes back against you. So I wrote here, interestingly enough, the normal force is also the value that a scale would read if you were standing on it. Scales read not weight, they read the normal force, which is why a scale doesn't work in outer space. Your mass still exists in outer space, but you can't stand on a scale in outer space. What's it reading? The fact that the ground isn't having to push up on you at all. For this reason, the normal force is sometimes called the apparent weight of an object. Most of you have grown up all your lives. You guys with me? You guys not looking at a phone or anything silly like that? That would be foolish, wouldn't it? Most of you have grown up all your lives with the ground pushing back up on you. Most of you, Jordan, have grown up with a normal force equal to gravity. Gravity pushes down, normal force pushes up. So when you stand, you don't realize it, you take it for granted. The ground pushes up through your feet. The normal force equals mg. Or when you sit in a chair, you can feel the normal force pushing up through your body. Any good amusement park ride, all it does is it mucks around with the normal force. And that terrifies us and causes us to get that thrill that we get on amusement park rides. Because you take the normal force for granted. And that's why we call the normal force your apparent weight. An amusement park ride does not change weight, which is the force of gravity on you. What it does is it changes how heavy you feel, your apparent weight. It changes the normal force. You feel lighter sometimes and you'll scream and pay money for that. You feel heavier sometimes and you'll scream and pay money for that. If a person with mass M and weight W is in an elevator standing on a bathroom scale, and you know what? Let's make it, unless I say different, let's pretend all of our scales are physics scales. They don't read in kilograms, they weigh in newtons. Oh, if you do need to get to kilograms, divide by 9.8. But let's pretend they all weigh in newtons unless I say different. If the elevator starts at rest and accelerates up, what will the scale read? W? B, more than W? C, less than W? And convince me. Once again, we're going to vote. Once again, how high you hold your hand up is how sure you are of the answer. So if you're standing on a scale in an elevator and the elevator starts to accelerate up, will the scale read W? More than W or less than W? Who says A, the scale will just read W the same as it... No one. Who says B, more than W? Who says C, less than W? Who didn't bother putting their hand up and voting at all and next time has to make sure that they vote and pick something just to learn and follow along? Next time, make sure you try, okay? Anyways, okay, convince me. B is right. Convince me. Yep.
Well, if the measures the normal force and you're going up, the normal force is pushing something else.
You know what, Mickey? You're right. I think in this case, a picture is worth 1,000 words. A very specific type of a picture. You know what this is a good job for? I think I'm going to do a free body diagram. So here's my free body diagram. Okay? What are the forces acting on this object? Get the obvious one. What else? Okay, normal force up. Now, let's assume that we're right and that it is bigger. So I'll draw it a little bit longer. Fn. Could you write for me an equation Who's winning? Who's losing? So it's going to be winner, Fn, minus loser, Mg equals Ma. What did we say we feel as weight in these three forces? What's your apparent weight? Which of these three forces? Normal force, not Mg. So let's get the normal force by itself. How? Okay. So the normal force here equals Mg plus Ma, or Ma plus Mg, but I put Ma last for a reason this time. And then don't write this next bit down. Just watch. Brendan, all of you right now are not accelerating up or accelerating down. In other words, all of you right now are, don't cross that out, are that equation. All of you right now feel Mg, you feel the chair pushing back up against you, you feel comfortable with that because you've grown up with that all your lives. What if we start to accelerate up? Well, if that's accelerating up and it's positive, what can you tell me about your normal force, bigger or smaller than Mg? Well, if you're adding something, what happens to your answer, Shaq? If you add something, does it get bigger or smaller? You know what? So let's say this, comma, adding Ma, which is sitting there, as long as A is not 0, it's positive up. Adding Ma increases the normal force. There's my abbreviation for increases, an arrow pointing up. What's my abbreviation for decreases? An arrow pointing down. There, Mickey, I did no English. And I'll try and show you ways to give an answer without using English, both for my ESL students, but also because I think it's nerdily cool and clearer. I drew a free body diagram, and then Jordan, I said, there's the equation that describes normal force. As long as you have an acceleration, your answer must be bigger than it was before. Has to be, the laws of addition. Example 2 says, write a net force equation for the situation described in example 1. There, did it already. I chose to do that in my answer. What if you accelerate up faster? Would you feel heavier or lighter? Heavier. In fact, if you accelerated up at 9.8, you would feel exactly twice your weight. We would be saying you'd be feeling 1 extra G, a total of 2 Gs, but you're all used to 1 G already, so you'd be feeling 1 extra G. Example 3, a 35 kilogram student stands on a kilogram scale. Okay, this one's in kilograms, which reads normal force divided by 9.8. If the elevator accelerates down, hey, that's important. Sorry. If the elevator accelerates down at 2.25 meters per second squared, then A, find the normal force, B, the scale reading. This is an elevator question. You know what this is a job for? I think it's a job for a free body diagram. There's the person. I'm drawing the forces on the person, not the scale. What are the forces acting on this person? Get the obvious one. Is this person in free fall? Nope. So there must be a force up. Which force? The scale pushing up. But what did we say that a scale measures? So let's call it the normal force. Am I going to draw it bigger or smaller or the same size? Which way is this person accelerating, up or down? That means the biggest force has to be pointing down. That means the normal force is going to be smaller. I'll exaggerate it. Who's winning? So if I go winner minus loser, now it is mathematically, Brendan, far more convenient for me to let down be positive. In the last unit, if you're using d equals VIT plus a half AT squared, VF equals VI plus AT, and VF squared equals VI squared plus 2AT, if you're using those, Josh, be very fussy. Down will be negative, up will be positive. Be very cautious. Here in this unit, because we're going to eventually be dealing with more than one mass, it's much more convenient to let positive be the most convenient direction. In this case, down, the winner. So my equation, Josh, is going to look like this. Josh, who's winning? Winner minus loser, Not saying that you are, but who's losing? Josh? And that equals your net force, and your net force is always just plain old MA. Josh, what did part A want me to find? How would I get the Fn by itself? Can I do two steps at once? Here's what I'm going to do. I'm going to plus this to this side because I hate that negative in front of it. At the same time, if it's okay with you, Brendan, can I minus that to that side? And can you see I'll end up with mg minus ma equals Fn. And then don't write this next bit down. But normally, that's what you feel. Right now, all of you are feeling a normal force of mg. If we start to accelerate down, so when the elevator goes down, when the roller coaster goes down the hill, oh, now we're subtracting. What's that going to do to this answer? Make it bigger or smaller or the same size? Bigger, smaller, or the same size? What do you think? Smaller. So when the elevator accelerates down, do you feel heavier or do you feel lighter? Lighter. Has your mass actually changed? No. Has mg actually changed? No. What's changed? The normal force. And that lighter one in particular is the one that causes us to freak out. All of us have experienced when we feel heavier. That's why you like swing sets. At the bottom of the swing set, you feel heavier. But you're used to that. Kids from about the age of 3 or so are used to a heavier normal force. In fact, athletes, that's what you feel when you jump. You don't notice it at the time, but that's what you feel when you jump. You're used to that. We are not used to the normal force getting smaller. That's why we freak. And I think that's built into us in terms of our evolution. We were once in trees. I think when the normal force gets small, we assume we're about to fall and we're grabbing for the nearest branch. I don't know about you, but like when I go on the elevator, on the way up, meh. On the way down, holy smokes. That's what it is for me. I can on the way up, I can enjoy that part of things and say, yeah, you know what? I felt this being pushed down into my chair feeling plenty of times before. It's on the way down where you feel like you're going to fly off, even though you're still accelerating down, you feel like you're going to fly off and you grab, that's where I get my adrenaline rush. Oh, let's find the normal force. Mass is 35. G is 9.8, not negative. We decided down would be positive in this question. Minus 35 times, what's the acceleration? 2.25. I get, to 3 sig figs, I guess 264 newtons. B says, find the scale reading. How much would this person feel like they weighed? Normally they weigh 35 kilograms. How do I change a force into kilograms? What's the conversion factor? Okay, so I'm going to go normal force divided by 9.8, and I still have that on my calculator. Thought I did. Clear. Divided by 9.8. This person would feel like they weighed 27 kilograms. 26.96, so 27.0 if you want to go to 3 sig figs. They'd feel lighter. Okay. Air resistance. Air resistance is the force of air molecules bumping into an object that's moving through the air. Air resistance always has direction that is opposite to the direction of motion, which is why it's a very complicated force. It's also a very complicated force because air resistance changes. You may have noticed when you stick your hand out of the window of a moving car, when do you feel the biggest force? When you're speeding up or slowing down? Okay, the faster you go, you feel a much bigger force against your hand, Jenny. That means air resistance also depends on velocity, which is why we won't look at it properly in Physics 12, to analyze air resistance, you really need calculus, because you need to be able to handle an equation where you have several different functions changing at the same time. We're going to temporarily, sort of, treat it like friction. Example 4 says, draw force diagrams for each of the following. So what we're going to do is we're going to throw a ball in the air. Here it is. Diagram A is while it's in my hand and I'm throwing it, so just before the release. Diagram B is after it leaves my hand on the way up. Diagram C is on the way down. Oh, and it says for B and C, include air resistance. Okay, let's look at situation A. What are the forces acting on situation A? Get the obvious one. Gravity. Now let's draw it in. When I do this, before I let go, which way is the ball accelerating? Up, down, or not accelerating? Up. So there has to be a force up, and I should draw it bigger than mg. Which force is that? You could call it normal force if you wanted to say it was a surface. Because it's a human being, traditionally I call it the applied force. To throw something, you have to apply a bigger force than mg. Watch. Look up. I just applied a force to it. Did the ball leave my hand? So, oh, you know what? F applied was smaller than mg. I would have to have a diagram where mg was longer and F applied was smaller. It's doable. But to get it out of my hand, F has to be bigger than mg. Okay, while it's on the way up, what are the forces acting on it? Get the obvious one. What else? It says include air resistance. Which way will I point air resistance? Okay, on the way up, air resistance is going to also be pointing down. I'll put it beside because it's awkward to have two arrows overlapping. And I know enough about projectiles to know that air resistance is smaller than mg for a ball. Not for a parachute, but for a ball. On the way down, what are the forces acting on it? Get the obvious ones. mg down. What else? Air resistance which way? Pointing up. The air is slowing it down a little bit. Not much, because a ball is fairly aerodynamic. But Mickey, for a parachute, we actually get these two to be equal. We get air resistance to be the same size as mg so that the parachutist is no longer accelerating. Eventually I jumped out of an airplane. So that when I jumped out of an airplane, hit terminal velocity with a safe speed, not a fatal speed. Pardon me? I don't know, mate. In example 5, it says this. In example, so you folks all turn the page. I'm going to scroll back to the diagram so you have it in front of you. It asks, how can situation B, how can the ball be traveling up if all the forces are pointing down? It's not. Otherwise, that would have appeared in the Jordan said it still has the applied force on it. No, that would have appeared in the diagram, and it doesn't. How can I be traveling up, yet still have all my forces pointing down? What about velocity? Rafi, F equals what times what? The basic equation for force. F equals? M what? MA. Now, so which way is the acceleration pointing in diagram B? Diagram B, which way is the acceleration pointing? Down. Does the velocity have to be pointing in the same direction as the acceleration? No. In fact, when you're in a car and you hit the brakes, your velocity is forward, but your acceleration is backward. And what I want you to realize, and this is something in Physics 11 kids really struggle with, and I want to lovingly beat it out of you, velocity and acceleration are independent of each other in terms of direction. Now, eventually, If I continue to accelerate down, eventually my upwards velocity will cancel out and start accelerating down. If I just let time run long enough, eventually velocity and acceleration do end up in the same direction because the acceleration is the direction of the change in velocity. True enough. But for now, I would say V equals up, accel equals down. V and A don't have to be in same direction. And this is really my way of saying don't get velocity and acceleration mixed up, which for someone without a physics background happens all the time. Now, the nice thing is your bodies have built-in accelerometers. You can feel acceleration. You notice it when you're on rides. The only problem is, Nate, they work totally backwards. Nathan, have you been on the elevator before? Okay. When the elevator shoots you up, which way are you clearly accelerating? Which way does it feel like your stomach is moving, though? Ah. And when the elevator shoots you down, which way are you clearly accelerating? But which way do you feel like you're about to fly? Up. When you're in a car and they hit the brakes, which way are you accelerating when we hit the brakes? Backwards. Which way does your body feel like it's getting thrown? Forwards. Okay? Or when you're in a car and they floor it, which way are you clearly accelerating? Forwards. But which way does your body feel? Okay. Your body has a built-in accelerometer, folks, but it's backwards. It just is. How many of you have ever gone on the Music Express ride at Playland, the one that goes around in a circle really fast? Okay, so you ready? Which way do you feel like you're being pushed on that ride? Outwards, to the left. So which way are you accelerating when you move in a circle actually? Always inwards, always inwards. We'll talk about that when we get to circular motion. But if you're moving in a circle, you'll swear you're accelerating outwards, but that's because your bodies have a backwards built-in accelerometer. You are accelerating inwards. Example 6 says, if the ball in example 4C is speeding up, write a net force equation. Okay. In example C, who's winning? Who's winning? MG. Who's losing? So on the way down, a net force equation would be winner take away loser. That equals MA. That equals MA. Example 7. A 90-kilogram parachutist free falls for a time and then opens a parachute. If the parachutist slows down at a rate of 1.5 meters per second squared, A says, compare the forces that act on the system. That's a fancy way of saying, draw a free body diagram. Okay. There's the parachutist. What are the forces acting on him? Get the obvious one. Okay, gravity down. What else? Yeah, you call it F parachute, but since part C says find the force of air resistance, I'm going to say I think they want me to call it air resistance. Am I going to draw air resistance bigger, smaller, or the same size as mg and convince me? What word did I underline? Which way am I accelerating if I'm slowing down? Josh. Up. So, for a second, I'm actually accelerating up. Does that mean that I'm moving up? No, I'm still moving down, but I'm accelerating up because that's what slowing down means. It means the acceleration is in the opposite direction of your motion. So, am I going to draw air resistance bigger, smaller, or the same size as mg? Which way am I accelerating? Up. So what direction must the winner be? Up. So am I going to draw air resistance bigger, smaller, or the same size? Okay? Now, don't write this down for the next second. As I slow down, what happens, this is why we don't look at air resistance because it's very complicated. As I slow down, as I decelerate, what happens to the force of air resistance? It gets shorter and shorter and shorter and shorter, and then you reach the magic, don't write this down, equilibrium point where air resistance and mg are the same. And this is also called terminal velocity, but the idea is for a parachute, terminal velocity is survivable as opposed to straight free fall, because air resistance for the parachute is a much bigger force than for a human body. So comparing the forces, there it is. B says, write a force equation. Okay. What would my force equation here be? C says, find the force of air resistance. Oh, let's get the F air by itself. Okay. How would I get the F air by itself? I mean, the nice thing, Grayson, is the equations are never going to be that ugly. It's just the getting of the equations is the tricky part, but the actual get the stuff by itself is almost always going to be plus or minus some things and maybe once in a while divide, right? By the way, look up, don't write this next bit down. What happens when I hit a constant speed and my acceleration is 0? What can you tell me about air resistance and gravity? They are there's my terminal velocity, okay? But we can go further than this. Mass, what did I say, 90? A is 1.5. We took care of the plus or minus in our winner minus loser. Plus 90 times 9.8. You get 1,017. If I go to 3 sig figs, I'll go 1,020 newtons. This also explains why you have to open your parachute a certain distance above the ground. It takes time for that equilibrium to occur. Initially, you decelerate really, 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 really fast, but your rate of deceleration is changing. As you slow down, air resistance gets smaller, and you're not decelerating as fast. So that's why you can't open your parachute, 200 feet above the ground and survive. You got to open it a certain amount of time before the ground to safely be able to decelerate. The force of air resistance is actually not a constant value. I've said this already, but I'll say it again. In fact, the force gets larger as speed increases. You notice that if you ever stick your hand out of the window of a moving car and you do the whole turn your hand sideways, and it also depends on the cross-sectional area that you're presenting to the direction of travel. A falling object will eventually reach the point when air resistance equals the weight of the object, where the force, that shouldn't be if, where the force of air resistance. At this point, it reaches what we call terminal velocity. Example 8. A parachutist jumps out of a plane and free falls, okay? They reach terminal speed and they maintain that speed for a while, okay? Then they open their parachute. They quickly reach a different terminal speed and descend to the ground. Sketch, we're going to cross out the word velocity, and above it, can you write the word speed? And the reason is, if we were doing velocity, what direction are we always traveling if we jump out of an airplane? Which means my velocity would always be what, positive or negative? I don't want to draw below I want to draw a graph above. So we're going to graph speed. Okay? So here is our speed versus time. And in fact, what we're really talking about here is vertical speed, because I know when they're in the airplane, they are traveling horizontally, and I'm going to pretend they're starting at rest. Okay? What did I say we're starting out at? So here's the plane traveling in a straight line. I haven't jumped yet. I jump. Ah! what happens to my speed? Okay, so something like this. Well, you know what? I'm not sure whether it's a curved acceleration. In a vacuum, it would be a straight line acceleration because the acceleration is constant. But with air resistance, as you speed up, your air resistance increases. To be very honest, if I was being fussy, I think it actually looks kind of like that. And there's your new terminal velocity. The faster you go, the slower you accelerate. So now I fall at terminal velocity. There's the horizontal line. And I pull my parachute. Now what? My speed decreases. Again, I think it would decrease really quick, very fast initially, and the rate of decrease would decrease. I think it would look like this. Big decrease, and then there's my new terminal velocity. Parachute drifts for a while. And then I get to the ground. Once I hit the ground, what happens to my speed? Something like that. My time scale is all whacked because I have free fall taking longer than the actual drift down. I'm just interested in the shape. Does that make sense okay? It says explain for each section of the graph in a few words what's happening to the object. I think we did as we did this together, so I think we're good. Next, some homework first of all. Number 1. Number 2. 3 is good. 4 is good. 5 is good. 6 is good. So far I've assigned everything, I know. Spaceship, we'll do 7. Skip 8, 9 is good. Ten is tricky, okay? 10, I would say, probably is more work than I would give you in one question on a test. Each part of it, to me, is totally fair game, and the overall concept of number 10 is fair game. It's just a long question with an A, B, and C. I would probably give you one extra piece of information because it's going to be a lot of, but see if you can figure it out. Skip 11. 12 is good, spaceships. Woohoo! We'll pause there.